Okay, good morning, students. We'll continue our discussion. So, yeah, for the tutorial class, so the tutorials class will be held on Mondays from 1 to 2 p.m. So, your first tutorial class will be this coming Monday, and I'll send the tutorial sheet by tonight. So, we were discussing about the norm linear space of all bounded linear operator from x to y, and we saw that bxy is a norm linear space with the norm that we have defined for operator. Now another result is that let x and y be norm linear spaces. So if y is complete, then the norm linear space bxy is also complete. Let's try to prove this. So note that x need not be complete. So if you only assume that y is a Banach space and x is any norm linear space, then bxy will be a Banach space. So to prove this, we have to show that every Cauchy sequence in bxy converges. So suppose we take any Cauchy sequence. So let Tn be a Cauchy sequence in bxy. Then we have to prove that this Tn will converge to a bounded linear operator T. First, we have to think how we can define the limiting operator T, and then we have to show that it is actually a bounded linear operator, and this Tn will converge to T. So, if we have any Cauchy sequence, then by definition, given greater than
For
0.
every fixed x, like if we fix an x, then t and x will be Cauchy.
Right, exactly. So that is the idea that for any x in x, we will see that T and x will be a Cauchy sequence, and therefore, and that is a Cauchy sequence in y, and therefore it must converge to some point in y. So that is how we will define T of x. So given epsilon greater than 0, there exists natural number capital N such that norm of Tn minus Tm is less than epsilon for all nm bigger than equal to capital N. So therefore, for any x in x, if we look at norm of Tnx minus Tmx, we know that this is less than equal to norm of Tn minus Tm times norm x and this is less than epsilon times norm x. So in fact, if you want to show that Tnx is a Cauchy sequence, then you have to make this less than any given epsilon prime. So you can choose epsilon equal to epsilon prime by norm x if x is non-zero. If x is 0, then of course this is equal to 0. So this is true for all nm bigger than or equal to capital N. So it follows that Tnx is a Cauchy sequence in Y for every x in X. Since Y is complete, this Tnx converges to some point in Y. So we define T from X to Y by T of X is equal to limit of Tn of X. Right. So now this is a well-defined map. What we have to see is that this is this map T is linear and it is also bounded. So if we take any say then T of any say alpha x1 plus beta x2, this by definition is limit of Tn of alpha x1 plus beta x2. And because Tn is linear, this is equal to limit of alpha Tn x1 plus beta Tn x2. And because Tn x1 converges to T of x1 and Tn x2 converges to T of x2, therefore this will converge to alpha T of x1 plus beta T of x2. So this implies that this T is linear. Also, we have to see that T is bounded. So for that, we have to see that norm of Tx is less than equal to some constant times norm of x. What we know is that these Tn forms a Cauchy sequence. So since Tn is a Cauchy sequence, we know that any Cauchy sequence in a metric space is bounded. So it must be bounded. Therefore, there exists some m greater than 0 such that norm of Tn is less than equal to m for all n. So therefore, norm of Tn of x, this is less than equal to m times norm x for every x in x and for all n. So norm of Tnx is less than equal to m times norm x. So if we take limit as n approaches infinity, we know that Tnx converges to T of x. So we will get norm of Tx is less than equal to m times norm x. This is true for every x in x. Right? So this is because we know that norm is a continuous function. So we can take limit inside the norm, and then limit of Tnx is T of x, and therefore we get this. Is it clear? So this implies T is a bounded linear operator. Now only thing we have to see is that Tn converges to T, which means that norm of Tn minus T goes to 0 as n goes to infinity. So I think the display has stopped. So let me see. Okay, so we have got that T is in Bxy. Now we will show that claim is norm of Tn minus T. This goes to 0 as n goes to infinity, which will imply that the sequence Tn converges to T. So this is again easy. So for this we have to make this norm to be less than epsilon for n large enough. So let epsilon greater than 0 be given. Then we have seen that there exists capital N such that norm of Tn minus so let's write the norm of Tn of x minus Tm of x and norm of Tn minus Tm can be made less than epsilon. So this is less than epsilon times norm x for all Nm bigger than equal to capital N. So now if we choose any n bigger than equal to capital N and then take the limit as m goes to infinity. So in fact, I can take this x in the unit ball only. So then I can write this as this is true for all x belonging to the closed unit ball of x. So in B of x, and norm Tn minus Tm can be made less than epsilon. So therefore, fixing n bigger than equal to capital N and taking limit as m approaches infinity, we get norm of Tn of x minus the limit of Tmx is T of x, and this will be less than equal to epsilon for all x in Bx, right? But the supremum of all these x, so this will imply norm of Tn minus T is less than equal to epsilon for all n bigger than equal to capital N. And this implies T converges to T. Right, so we have got that if Y is a Banach space, then T of xy will be a Banach space for any non-linear space X. So as a corollary to this, we get that the dual for any Banach space X is dual X star is a Banach space. So this is because Y is equal to R or C is complete X star equal to B of, sorry, I don't even need X to be Banach space. So I should say that for any non-linear space, any non-linear space, X, its dual is a Banach space. So this Bx Y is complete. So this is one important result, that dual of any non-linear space is always complete. Okay, so what we have seen is that Bxy is a non-linear space if X and Y are so. So in particular, if I take X and Y are equal, so we have seen that B of X is a non-linear space if X is a non-linear space. Also, Bx is a Banach space if X is a Banach space. This is again a particular case of the previous one, because here we are taking bonded linear operator from X to X. So if X is complete, then Bx is also complete. Uh, so that means that B of X is a vector space, and we can define a norm, and it becomes a complete norm linear space. So on B of X, we have addition and scalar multiplication. So we have vector space operation. There is another operation which can be defined on B of X. So note that we can define a multiplication operation on B of X. So what is this multiplication? So this is just composition. So if we have if T1, T2 belongs to B of X, then T1, T2 is nothing but T1 composed with T2. This is composition. So this T1, T2, this is also in B of X. So if we look at, so first of all, clearly T1, T2 is linear. So composition of any two linear transformation will again be linear transformation. Also, if we look at T1, T2 of X norm, so this is equal to T1 of T2X, which is less than equal to, because T1 is the bounded linear operator, this is less than equal to norm T1 times norm T2 of X. And T2 is again a bounded linear operator, so this is less than equal to norm T1 times norm T2 times norm X. So therefore, T1, T2 is a bounded linear operator, and we get that norm of T1, T2 is less than equal to norm T1 times norm T2. Right. Also, you see that with this multiplication and the vector space operation, this B of X becomes what is known as an algebra. So we have addition, scalar multiplication, and also multiplication defined on this, and it satisfies all the property of algebra. For example, you have distributive law. So if you take T1 times T2 plus T3, that is same thing as T1 T2 plus T1 T3, and other properties of algebra are also satisfied. And this is one property that if we take the norm of product of two element here, then it is less than equal to product of the norm. So this is called less, that this norm is the submultiplicative norm on Bx is submultiplicative. You can see by some example that it can be strictly less than norm T1, T2. So it need not be equal to the product of the norm. And we have the identity operator on Bx, which acts as multiplicative identity on this. And what is the norm of the identity operator? So if I is the identity operator, then it is easy to see that norm of I is equal to 1. So norm of the multiplicative identity is equal to 1. So this is actually B of X is what is known as a Banach algebra. So I'm not defining in general what a Banach algebra is, but Banach algebra will be So X is a Banach space, and there is also a multiplication defined so that it forms an algebra, and the product, the norm of the product. So if X and Y are two elements, then norm of XY is less than equal to norm X times norm Y. And I mean, in general, Banach algebra may not have this identity element, but if it has, it is called a unital Banach algebra. So, then the norm of the identity element is assumed to be 1, and we have this. So, here the X is assumed to be a Banach space. So, yeah, X is a Banach space. Okay, so next we will try to show that
सर आवाज नहीं आ रही है आपको?
yeah, so let me next define what we mean by two norms being equivalent. So, definition: two norms on a vector space X are said to be equivalent if the topologies induced by them are the same. So, we are defining what we mean by two norms being equivalent if the topology. So, we know that if we have a norm, then this becomes a metric space and a topological space. So, if the topology coincides, metric can be different, but the topology is same, which means that every open set with respect to one norm is also open with respect to the other norm. So, then we say that the norms are equivalent. And there is an equivalent criteria. So, theorem. Let X be a vector space and let norm 1 and norm 2 be norms.
स्क्रीन नहीं दिख रही,
Sorry,
स्क्रीन नहीं दिख रही सर.
no, it is visible on my. Is it visible to others?
Yes sir.
You may be having an internet connection problem. So suppose X is a vector space and norm 1 and norm 2 are two norms on X, then these are equivalent. The two norms are equivalent if and only if there exist constants C1 greater than 0 and C2 greater than 0 such that for all X in X, norm of X in the two norm, this is less than equal to C2 times the one norm of X and bigger than equal to C1 times the one norm of X. Right? So this can also be taken as the definition of two norms being equivalent. If there exists constant C1 and C2, both positive, such that norm of norm 2 of X is less than equal to C2 times norm 1 of X and greater than equal to C1 times norm 1 of X, then these will be equivalent. So let's prove this. So what is the meaning of the topologies induced by norm being equivalent? So note that the topologies induced by norm 1 and norm 2 coincide if and only if and only if the identity map, so identity from X with norm 1 to X with norm 2 is an isomorphism. So I did not define isomorphism. So let me say what is an isomorphism. So T from X to Y is said to be an isomorphism if T is so first of all T is linear, bijective and T inverse also I should say T is bounded. So and T inverse is bounded. So in linear algebra, when there are two vector spaces, then we say that T is an isomorphism. If T is a linear transformation, it is 1 1 onto. So then we say that it is isomorphism, right? So in that case, you can define T inverse from y to x, and T inverse is automatically linear if T is assumed to be linear. So here, because we are on non-linear space, so we consider all bounded linear operator from x to y. So a bounded linear operator from x to y is said to be an isomorphism if it is 1 1 onto and T inverse is also bounded. So you you will see that just assuming that T is bounded linear operator does not imply that T inverse is bounded. So this is an extra condition which is needed for T to be an isomorphism. So first of all, why is this true? So if we have two topologies, in fact, if we have two topological spaces x and y, then we say that these topological spaces are isomorphic, or in that case it is called homeomorphic, if we have that there should be a homeomorphism from x to y, right? So it should be a continuous map, and the inverse is also continuous. So in this case, we have the same space, but have two different norms. So there is one topology on this x and another topology given by a norm 2 on x. So if these two topologies are the same, then if we take the identity map from x to x with these two different topologies, then it must be continuous, because if I take any open set in this codomain space, so with respect to norm 2, if I take any open set, then its inverse image under the identity map is that same subset, and if we want the topologies to be same, then it should be open in this one also. So that will show that this identity map is a continuous map. And conversely, if I have any open set with respect to norm 1, then its image is again that same set. So it should be open here. So if the two topologies are same, then the identity map must be an isomorphism. And if this identity map is an isomorphism, then again, if I take any open set with respect to two norm, then its inverse image under identity map is that set. So it must be open with respect to one norm also, and vice versa. So this is very simple. Now, what is the meaning of this identity map being a bounded linear operator? So identity from x norm 1 to x norm 2, this is bounded if and only if so if we look at x with norm 2, that is same thing as identity of x norm 2, and because identity is a bounded linear operator, this is less than equal to some constant, say c2 times norm x 1 for some constant C2 positive. So we get that norm x2 is less than equal to C2 times norm x1, and the inverse is also bounded. So I inverse from x2 norm 1 to x2 norm 2. This is bounded. This is if and only if. If we look at norm of x1, this is I inverse of x norm 1. So this has to be less than equal to some C1 times norm of x2 for some C1 positive, and this will imply norm of x2 is bigger than equal to 1 by C1 times norm x1, right? So norm x2 is bigger than equal to some constant, positive constant times norm x1, and norm x2 is less than equal to some constant times norm x1. So
I inverse should become
sorry,
norm 2 to norm 1. So, I inverse will be a maximum norm 2 to norm 1. Okay,
yeah, norm 2 to norm 1, right? This is from norm 2 to norm 1, and this is bounded, so therefore we get that x is I inverse of x norm 1, right? Okay, so let's see an example. So we have seen different norms on Rn, right? So if we look at Rn or Cn with say these two norms, so norm 1 and norm infinity are equivalent on Rn or Cn. So how do we prove this? So we can just show that there exist constants like that. So if we look at norm of x1, so if x is equal to x1, x2, xn belonging to Rn or Cn, then norm of x1, this is equal to summation of mod xi I equal to 1 to n, and this is of course bigger than equal to maximum of mod xi I from 1 to n, and this is what we have defined as the infinity norm of x. So we get that norm of x1 is bigger than equal to infinity norm of x. Also, we have to show that this is less than equal to some constant times the infinity norm. So norm x1 is equal to summation of mod xi I equal to 1 to n. This is less than equal to n times the infinity norm of x, right? Because each term is less than equal to the maximum of mod xi, So it is less than equal to n times. So therefore, we get that norm x1 is less than equal to n times norm x infinity and bigger than equal to norm x infinity. So these two are equivalent. Similarly, you can see that norm 2 is also equivalent. Another thing is that if we have say 3 different norms, and suppose norm 1 is equivalent to norm 2 and norm 2 is equivalent to norm 1, then norm 1 and norm 3 will also be equivalent. Right? That is again easy. So this equivalence of norm, this is in fact an equivalence relation. So, oh, so, or you can try to show that norm 2 and norm infinity are also equivalent, right? So maybe exercise so that norm 2 and norm infinity are equivalent norms on Rn or Cn. So note that all these things I am saying on this finite dimensional space Rn or Cn. It's not on the sequence space LP. So on that they will not be equivalent. So in fact, what we will see maybe in the next class, that on any finite dimensional vector space, any two norms are always equivalent. So after we have done that, then all these things are corollary, that if we take any two norms on Rn, then they must be equivalent. Right? So we will show that any two norms on a finite dimensional norm on a finite dimensional vector space, they are always equivalent. So before doing that, okay, so what let me show this. So let T from Rn with norm 1 to R with Rn with some norm be any linear transformation where norm 1, you know what it is, and this norm is any given norm on Rn, then T is bounded, or equivalently T is continuous. So any linear transformation from this So in fact, after we have proved the general result, if we take any two norms, then it must be A equivalent. But here I am taking this one norm and this. So here again, norm x1 is summation of mod xi I equal to 1 to n. So to prove this, if we have any t, yeah, so I have to prove that this is bounded. So if I take any x belonging to Rn, x is equal to summation of xi times ei I equal to 1 to n, where this ei is the standard basis vector. So ei is equal to one at the ith place and all other 0. So then t of x will be equal to summation of xi tei I equal to 1 to n, because t is linear. So norm of tx this is equal to norm of summation xi t of ei. This is less than equal to summation I equal to 1 to n mod xi times norm of tei. So we have te1, te2, ten. So we can write this as less than equal to maximum of norm tei I equal to 1 to n times summation of mod xi, that is norm of x1. So norm of tx is less than equal to this constant times norm x1. So therefore, norm of tx is less than equal to m times norm x1 for all x belonging to Rn, where m is equal to maximum of norm tei. So this is a constant, and this by definition implies that t is a bounded operator. Right. So here this norm, it can be any norm. In particular, if you take 2 norm or infinity norm on the right hand side, then this will be any linear transformation will be a continuous linear transformation. So let me stop here. In the next class, I'll show that on any finite dimensional vector space, so any two norms are equivalent. And
Sir, here M is not fixed, right?
sorry?
M is not fixed, depend on the basis, no?
No, M is fixed, right?
We can change EIs and
EIs are fixed.
we
E1,
can change
E2, En.
and we take another basis for Rn.
Sorry?
Instead of this basis EIs, we
Uh-huh.
can consider another basis for Rn, and then we can write X as that linear combination. Then
Yeah, you can do that. Yeah, so I mean, this EI does not have to be standard basis, right? If you choose any basis, then you can do the same thing and you get constant. But what is the
yes,
problem?
that's what as I am saying that M is not fixed, right?
No, M is never fixed, right? If I say that norm Tx is less than equal to M times norm X, is M fixed? Is M always constant? I mean, one fixed number. Instead of M, I can take anything bigger also, then also it will be true, right? So
Yes.
I'm not saying that this M is equal to norm of T, that it will be fixed, right? I have to just find one constant such that norm Tx is less than equal to that constant times norm X, right? So fixed in the sense that it does not depend on X, right? Here I need to get that this should be independent of X. So you see it does not depend on X, right? But yeah, what you are saying is that if you choose some other basis, then instead of this TEI, it will be T of VI, where V1, V2, Vn is a basis for Rn. So that is okay. But to do the proof, you have to like fix a basis and then do it. Yes.
Sir,
Any other question?
Like so,
sir,
this will be like the maximum over all columns, the norm of every column of like the matrix representation of T.
Exactly. So this the thing is that if you think of this linear transformation as matrix, because you know that if we have on finite dimensional vector spaces, any linear transformation uh, can be described in terms of matrix. There is matrix of linear transformation. So if we take the standard basis, then you get matrix, and this TE1, TE2, TEN are nothing but the columns of the matrix A, right? So what we are doing here is that uh, taking the maximum of norm of TEI, so that is the maximum of the norm of the columns of this matrix, right?
Like even if we take a different basis, say V1 up to Vn, and
Right.
if I then take the representation of T in the new basis V1 up to Vn,
Right.
then I can still bound it by columns because the proof will go through even with the different basis. So
Right.
uh,
True. So oh,
basically, in like we can upper bound the norm by taking a representation, any matrix representation, and taking the maximum norm of columns.
exactly. If your T is this, I mean, if you are taking that on the domain space, you are taking the one norm, right? So this summation of mod xi, this norm, if we are taking, then your norm T is always less than equal to the column norm of this, right?
sir,
Yes.
sir, can we change the image set from Rn to any other set, like any other non-linear space?
You can change this to any finite dimensional vector space. Not any, but if you assume that here instead of Rn, suppose I take any x with norm, where x is a finite dimensional vector space, right? So then okay, here because on the domain space I am taking finite dimensional, then of course the range will be finite dimensional only. So yeah, so if I take any non-linear space, the range space will be finite dimensional, and in that case we can do the same thing. So you will do the same thing, that you write x equal to summation xi ei, and tx is summation xi t ei, and this same proof will go on. Right. So here the right hand side, it can be any vector space.
Okay, sir.
So yeah, maybe let's write this as remark. Note that the above lemma is true if we take T from Rn with norm 1 to X with norm for any non-linear space X. Right. In fact, you can see that on the domain space also, if I take any finite dimensional vector space, then there is a way to define norm 1, right? So if you take any finite dimensional vector space and fix a basis, then every element can be written as summation of alpha I times vi, where v1 v2 vn is basis for that finite dimensional vector space, and then you can define a norm on that to be equal to summation of mod of alpha I. So of course, this norm depends on the basis, just like when I define on Rn, this norm 1, it is with respect to this standard basis E1, E2, En. So same thing you can do for any finite dimension vector space, and you can define a norm 1. And then if I have any V here with norm 1, and here I have any vector space with any norm, here again, this Rn is not important. I can take Rm also, and that will also go through. So. Okay,
Sir,
so
in this case,
yeah,
I think this capital M will turn out to be the norm exactly, because if I choose my x to be 0 everywhere, but it's 1 in the index where norm ti is maximum. So I choose I where norm ti is maximum, and I put a
right.
1 there and 0 at all other positions. Now I compute norm tx. So norm tx will just be xi times norm of xi times ti, because all the other x days are 0, and that will be, so xi is also 1, so it's just norm tei, which is capital M itself.
Yeah, I mean you can do that. So you feel like want to prove that what is norm t, that can also be done. But here, I mean, we were only interested in showing that this is bounded. I mean, you will see
Yeah.
why I have written this lemma. So basically, what I want to show is that so you know that on Rn, when we take the usual metric or the usual topology, then we have a characterization of compact subset, right? It's a subset is compact if and only if it is closed and bounded. So this is true if we take the Euclidean space Rn. So now by using this result, you will be able to see that if we take any norm on Rn, then also if I take any closed and bounded subset with respect to that norm, then it will be compact. So in particular, the closed unit ball is compact in any finite dimensional, and then you will see that we can replace this Rn by any finite dimensional vector space, and still I can say that same thing. So that is something, and the, we will also show that this actually is true only for finite dimensional. So on infinite dimensional, the closed unit ball cannot be compact. So that is again one important result that we will prove later. that non-linear space is compact. A non-linear space is finite dimensional if and only if the closed unit ball is compact in that. So our next class tomorrow is a holiday, but Saturday is working as Friday's timetable. So our next class will be on Saturday at 11 o'clock.
For infinite dimensional,
Yeah, go ahead.
for infinite dimensional cases, means this is not true then.
What is not true?
This theorem.
No. So on infinite dimensional, okay, next class I'll give an example also where you can have two different norms which are not equivalent. So and it is not very difficult. You can try to like construct also, but
Okay.
I'll do that next time.